Good morning. My name is Rachel Harvey, and presenting with me today is Rachel Cueva and Peter Menev. We will be discussing our project, Robotic Habitat Technologies for Minimizing Crew Maintenance Requirements as members of Gemstone Team Astro from the University of Maryland. We'll begin with an introduction and brief overview of our design robotic system, then discuss experimental testing and validation, and then go on to our proposed flight design and finally conclude with programmatic logistics. Now for our introduction and system overview. Since 2000, the International Space Station has been continuously crewed. Astronauts' primary activities include operational tasks, changing samples, conducting experiments, logistics and stowage, as well as maintenance and repair tasks. 12% of crew time is spent on operational and logistics tasks, as well as managing cargo transfer bags. Approximately 16% of crew time is allocated to maintenance and repair tasks. With the International Space Station being continuously crewed, this work time allocation is feasible. However, time spent on operations, logistics, repair, and maintenance is detrimental to completing scientific experiments. Unlike the International Space Station, NASA's Lunar Gateway will go uncrewed for 11 months out of the year. The Lunar Gateway will allow humans access to the lunar surface and enable deep space transport to Mars. Without constant crew members on board station, dexterous robotic systems must be implemented to complete essential maintenance and operational tasks. Our robotic system is designed to meet the needs of NASA's Lunar Gateway while adhering to the requirements of RASC-AL Theme 5. Our Level 1 requirements are as follows. The system shall be ready for launch by the mid-2020s. The system shall not cost more than $2 million. The system shall perform maintenance and repair tasks on the Lunar Gateway, and the system shall include anomaly detection capabilities and necessary situational awareness. All of these will be verified by analysis, and then our M3 and M4 system requirements will be verified by analysis, test, and technology demonstrations. Stemming from our Level 1 requirements, our Level 2 requirements are as follows. The system shall utilize an existing, affordable, flight-certified dexterous manipulator as feasible. Our rationale for this is that using pre-existing robots and flight-certified hardware will allow for a reduction in both cost and time. Next, the system shall be designed using existing module standards for the International Space Station. This will provide us with detailed standards for testing. And then the system shall assume gateway architecture is substantially similar to the international standard payload racks. Once again, this will provide us with detailed standards for our testing and evaluation. Our robotic system aims to complete preventative maintenance tasks, corrective maintenance tasks, as well as diagnostic maintenance tasks. Our primary focus has been preventative maintenance operations, specifically the inspection of systems and hardware. And operations such as these may consist of flipping switches, turning knobs, pushing buttons, rotating and pulling on various electrical connectors. In the future, we hope to accomplish corrective maintenance tasks and diagnostic maintenance tasks, and these operations might look like repairing or replacing hardware, as well as evaluating problematic systems and hardware. Our design consists of utilizing a teleoperated two-armed dexterous robot, Ranger TSX, of the University of Maryland Space Systems Lab that travels along a T-beam rail. An end-effector exchange system is implemented on each dexterous arm to be used for various maintenance and repair tasks. Cargo transfer bag mockups have been designed with an April tag identification system, and mockups of international standard payload racks have also been created for testing and simulation purposes. Simply put, our concept of operations consists of sending a command to the robot and then watching it complete a specified task. Once the robotic system and rail mobility system have been integrated into Gateway prior to launch, they'll be monitored by mission control. After an operator recognizes an issue in station, they would send a command specifying a location, task needing to be completed, as well as the necessary end effectors and equipment. From there, the robot would autonomously collect the required components and propel itself along the rail to the site of the task. April tags would designate each cargo transfer bag, as well as various locations so that the robot would be able to move precisely. These images depict the dexterous arm retrieving a designated CTB and repositioning it via magnetic end effector. Mission control would be able to monitor the robotic system and verify the requested task was completed. For simplicity's sake in simulation, only one Ranger TSX arm has been utilized.
Hello, my name is Peter Manet, and I will now present the experimental testing and validation section. First, allow me to introduce you to the three main systems we have at our disposal. First is Baxter Research Robot. It is a pair of two 7-degree of freedom manipulators on a fixed platform. It's primarily used for preliminary task force tests and CTV manipulation testing. It has a camera at the end of each arm. It proved to be very useful for visual servoing type tasks. Next is MBV. It is a 6-degree of freedom manipulator. It's quite robust and was used for a routine task force utilization experiment. Finally, there is Ranger TSX. Ranger TSX is a system that is suited for ground, underwater, and space operation. It has two 8-degree of freedom arms attached to a single positioning leg. In fact, RTSX was designed for a space shuttle flight experiment and approved by the NASA Payload Safety Review Panel for flight and operations on the space shuttle. We intend to use it for further testing in the future to validate our current experimental findings. The team has created a task board that was used to evaluate robotic capabilities. It has a variety of features that mimic typical tasks that are conducted by astronauts on a daily basis on the space station. For example, switches with switch guards, buttons, valves, buckles, and electrical connectors. All of these tasks are fairly useful to have a robot system perform, as they can save quite a bit of time on a space station. Each of these tasks has an electrical indicator light that is turned on when the task has been successfully completed. If a button is pushed, the LED light will turn on. Next, the team has created a set of initial parallel jaw grippers. These were 3D printed using PLA, so they were pretty easy to make, but they were not the strongest. We also applied a few different coatings to them, like rubber and standard life materials, to prevent slipping between the grippers and the components they are trying to grasp, like the knob, and this proved to be sort of useful. Next, the team has created a mock-up of an international standard payload rack for full-scale system testing. It will be used for demonstrating CTB logistics capabilities, as well as complex robotic movements like pulling out drawers. Initial experimental results show that the robot is capable of pushing buttons, flipping switches, with or without guards, and in both directions. However, some tests were not as successful. The electric connector was unable to be pulled out due to the lack of a counterforce on the acrylic panel. The knob could not be turned due to insufficient robot torque from the end effector. In fact, the fingers just deformed. And some of them have not yet been tested, like the fluid connector and buckle, since they required two manipulator arms to be performed. Next, here we have a demonstration of a simple task being performed by Ranger and MBV with a double jaw gripper mechanism. It's being used as a simple push pin onto the button. And as you can see, the task is pretty quickly successfully completed. Next, let us take a look at a more complicated task where Ranger and MBV is attempting to put down a switch guard and then flip a switch that is beneath the switch guard. All the while, MBV is being controlled by an operator using a Cartesian controller joystick. They can also control it in Robotic using another joystick. They use both of these functionalities here to position the arm in such a way that they can be moved straight down to undo the switch guard. Once that has been completed, they will be able to go back and then perform the switching operation onto the active switch that's needed. Similar operations can be done with the other direction and or with a different switch that is just without a cover. You can see now it will start to go down. I'm going to flip that switch, and there we go. The operation was successful, and this test is completed. Alright, now let's move on to the second part of our testing. CTV manipulation testing, which was the logistical movement of cargo transfer bags between two different points. This involved the use of the Nicodrome electropermanent magnet EPM, cargo transfer bags, CTBs, and APRO tags. And the EPM is a electropermanent magnet that can be toggled on and off using a small electric pulse. It is not a constantly on electromagnet demanding current. What this does is it allows us to form a connection between the robot end effector and the cargo transfer bag. APRO tags that are placed on CTBs can enable precise position detection using cameras that are placed either on the robot arm itself or in the space station surrounding them, which is great for quickly positioning the arm in a good position next to them. Here, there's an image of a modified CTB mockup with an APOTAG. In this image, what is not shown is there's a small metallic plate underneath the APOTAG, which is what enables the connection between the the CTB and the end effector to be formed. Here, let's take a look at a video of Baxter performing a APOTAG-based movement to a CTB, and then being moved to a different location and depositing the CTB elsewhere. The operator is able to do this by using a GUI where they can enter a command to make the robot automatically position itself next to the APOTAG, and they can use the Move It Motion Planner to position the robot in Cartesian space to perform movements efficiently without having to move each joint individually, joint by joint. The start of the video, what will happen is the operator presses a command and the arm automatically moves itself down. Once it has reached the CTB, the Nika drone is signaled to turn on, the magnet is connected, and the CTB is now attached to the robot. Once that is done, the CTB is moved up, then to endeavor the position on the table and placed down. Once it has been set down, the Nika drone is signaled to turn off, which upon completion, which will allow the CTB to drop down onto the table, and the task is then completed. Now let's take a look at this in full speed. As you can see, this type of motion planning allows us to perform a rather complicated task within seconds. All right, that is all for our testing section.
My name is Rachel Cueva, and I will be presenting our proposed flight design. Since we selected a two-arm robotic system as our primary component, we also needed to design a mobility system for it to make its way around Gateway. We considered a few different options, such as a free-flying system, a cable system, and a rail system. The free-flying option was one of the heavier options at approximately 40 kilograms excluding payload, and this was based off of the Space Systems Lab Exospheres vehicle. Although this option would be highly mobile, it would be more difficult to implement autonomously, robustly, and safely. It would also require additional actuators and fixtures to stabilize the vehicle while conducting operations, which would further increase the mass of the system. Because of these factors, the free-flying system was ruled out. The cable system was inspired by the NASA Charlotte intravehicular robot. This system would allow for 6 degrees of freedom of movement, and the cables themselves would be lightweight compared to the other two options. However, the cables must be mounted to the boundary of the habitat, so the system would occupy the entire volume of space available. This would not only be extremely inconvenient, but could also be potentially hazardous for crew members on board the station. The rail option mass is comparable to the free flyer option at approximately 20 kilograms per module section. Its compact nature allows it to be easily out of the way of astronauts, and the beam-like structure would be more easily manufactured and assembled than the complex cable system. Its rigidity would also supply necessary forces and torques to stabilize the robot while performing operations. Ultimately, the rail design was selected due to its low risk and higher technology readiness. We considered two different rail designs for the mobility system, a T-beam and the other being a cylindrical beam inspired by the modern-day roller coasters. The T-beam is slightly lower in mass and volume than the cylindrical beam. It was also deemed more manufacturable than the cylindrical beam, and when mounted, the cross-section of the T-beam is smaller in profile and less protruding than the cylindrical beam. This means that it would be less likely for something or someone to snag on the rail. Because of these reasons, we decided to go with the T-beam as our final design. This image shows the dimensions of the cross-section and length of the T-beam. The length per module section is 8 meters, based off of the ISS Destiny module. The total cross-section is 11 centimeters in height, with a 20 millimeter thick web and 15 centimeter long and 10 millimeter thick flange. The robot would attach to the rail via a mount with wheels, and the wheels would be located underneath the flange and secured by the two smaller vertical side portions. Two different analyses were conducted on the rail design. A static case determined that the robotic system on board would deliver a max stress of 129 kilopascals to the rail, and a dynamic case determined that the first vibrational mode of the rail is 64.1 Hz. All operations and controls will operate at frequencies below this first mode in order to avoid all resonances of the hardware. One requirement of the Theme 5 was that our design had to have some sort of situational awareness and anomaly detection method. For situational awareness, we've implemented April tags to provide identification and localization data for equipment and cargo transfer bags on Gateway. These go hand in hand with cameras that will allow for visual detection of April tags and hardware on Gateway. We will also use accelerometers to measure vibrations on the rail system and the robotic arm. So if vibrations exceed levels that could either disturb science experiments or distract the crew, signals could be sent either autonomously or via teleoperation to correct this. As for anomaly detection, the implemented software will consist of various autonomous servicing algorithms that can be used for common and predicted failures. Unless a failure is absolutely time critical, human approval will be required before the algorithm is initiated. Unexpected failures are also guaranteed to occur, so for these instances, the human supervising the robot will be able to take control and teleoperate the robot to address the failure. This slide shows the breakdown of our overall system mass as well as the power requirements for the Ranger TSX robot. Our current best estimate for mass is at approximately 263 kilograms. As for power, the Ranger TSX system operates at 28 volts DC, with a peak power draw of 5 kilowatts and a maximum continuous operating power of 1 kilowatt.
Now, let's go over the logistics management GUI that was created to assist operators in performing strings of complex maneuvers without having to manually control the robot at all. The GUI comprises of 5 main elements. First is the Go to Delivery Wait button. What this does is it takes the robot to a predetermined position in front of the cargo transfer bag delivery bay. Second is the camera feed, which allows the operator to see from the robot's end effector's perspective. This allows them to do is it allows them to see which cargo transfer bags are available and how they are positioned relative to the end effector. The cargo transfer bags are labeled with numbers corresponding to their identification code, allowing them to judge which one they want to prioritize. 3. There is a drop-down menu and 2 buttons that allow an operator to select which CTB they would like to pick up. And then it also allows them to tell the robot to go to the April tag they've selected and then attach the cargo transfer bag once they have successfully approached it. 4 is the Go to Transit Position button. This does is it takes the robot into a semi-stowed position that is safe to travel between 2 different positions in the space station. Finally is the Set Drop-Off Location drop-down menu and buttons. The drop-down allows the operator to set an unoccupied drop-off location, press the Go to Drop-Off Location button to actually take the robot there, and once the robot has arrived there, attach the CTB and leave it there. Before we go in and take a look at this GUI in action, it's important to understand that complex motion planning and collision avoidance algorithms are in place behind this GUI. What this does is it allows the robot to create trajectory plans that factor in the robot's environment and ensure collisions between the robot and the robot's attached objects do not take place with these surroundings. So if the cargo transfer bag is attached and the robot is trying to take it out of the rack, what the robot will do is it'll construct a curved path that will take the cargo transfer bag up and out of the rack without touching anything else, like the shelf or the outlining walls of the rack. Now let's take a look at a video of this in action. So what this starts out with is the operator has selected April Tag 2 and has pressed the Go to April Tag 2 button. This does is it takes the robot to that position. Once the robot has arrived in this position, they will attach the CTB and then it will return to the deliver bay post. This is important to note because it is easier to go from the attached post to the transit post through this intermediate step because a complex motion plan like that is hard to generate. Now, once it is in the transit post, the operator sets the Go to Drop-Off Location button and has selected the Drop-Off Location 1, which will be the bottom right position on the rack. I've pressed Go to Drop-Off Location, and we are now waiting for the robot to arrive there. From this position, the robot will return to a pose that is in front of the rack so that it is easier to insert the CTB. It is hard to construct a motion plan from this stow position to inside of the rack. Instead, we do an intermediate step. This is all done in the gazebo simulated environment, which has been very useful during this time of campus closure, since we have no access to the real robot. Instead, we have been able to verify all of our algorithms and motion planning algorithms using gazebo. The robot is not identical dynamically, but it is a fairly good approximation. One thing that is not a good approximation is the rail speed, as a realistic rail would likely be much slower to ensure that it is a safe and feasible operation. Once the robot has returned, by pressing the Go to Delivery Bay button, which automatically puts into a stow position, so there's no need to worry about that for the operator. Instead, it just directly takes it back. The operator will then repeat this procedure with the other APROTAG 0, which is automatically populated in the field. Once they have attached it, they will press the Attach CTB button and return to the Delivery Bay pose. Select a different drop-off location 2, and then take the cargo transfer bag over to the other rack. This position will be the top right shelf. Let's fast forward to where it is already in front of the rack and positioning it on the shelf. You can see this time it will be a little bit different. The robot will go up and over the shelf in order to ensure that collisions are avoided. A similar procedure will be repeated for the third one, and we will fast forward through that one as well. This highlights is that this type of procedure is very easily performed by an operator despite the rather complicated positions and maneuvers need to be performed. It might not be as it is much faster than performing things joint by joint. Let's fast forward back to the first rack, grabbing onto cargo transfer bag 1, and selected the third drop-off location. There it is. Now it is attached. Let us fast forward to the drop-off. There we go. And similarly to the second one, we are going to go up and over and place it onto the shelf. There we go. And that's about it. Alright, so the final aspect of our design is maintenance and repair on Gateway. So some possible tasks that can be completed on Gateway, this is off of common repair tests completed by astronauts on the ISS, are the removal and replacing of electrical connectors and fluid connectors, disassembly and reassembly of malfunctioning life support systems, and end-to-end repair of something like an oxygen generator assembly, something that could be done inside of a mock-up rack that we showed earlier. So most of these tasks are something that we are definitely considering and have been working to modeling and demonstrating the capability to perform them with our robotic systems. However, we were not able to do so this semester due to the campus closure and research restrictions in place. Finally, some future work that we have also outlined so far is to finalize the construction of the International Standard Payload Rack for various testing. For example, we would like to use it for demonstrating complex CTB logistics management procedures. These procedures would involve a migrated Ranger NBV manipulator onto a wheeled base. In addition, we would like to have this done completely automatically using this APROTAG automation identification system and ensure that this is done rather quickly but still safely. Finally, we would also like to demonstrate more complex robotic movements, such as pulling a drawer out from a rack, and potentially even automate some basic tasks and interactions with the task board between the robot. So we feel that with these capabilities, our robotic system would be a very well-prepared robot for servicing a potential future space station.
So now moving on to programmatic logistics. Our proposed design consists of a few major key components that require technology advancement. Our two most developed technologies are the Ranger TSX robot and the End Effector Exchange System, which are both rated at TRL 6, meaning that they have been demonstrated in a relevant ground environment. Ranger TSX was designed for a shuttle flight experiment and was approved by the NASA Payload Safety Review Panel but never flew. And although we weren't able to do much testing with an end effector exchange system due to COVID, this type of system has been tested multiple times before in ground simulations, so we deemed TRL 6 appropriate. Our lowest TRL technology is the EPM end effector, since there are concerns regarding the brief electromagnetic pulses potentially interfering with sensitive technology on Gateway or in CTBs. So this piece of technology requires extensive testing in order to verify safety of use. This is our timeline for integration based on the NASA project lifecycle. Conceptual design will continue through 2021. Preliminary design and analysis will begin in 2022, with system requirement reviews and preliminary design reviews beginning in late 2022. TRL advancements will continue through 2023 until all technologies are at least TRL 6 for launch readiness. Critical design reviews will take place throughout 2023, and the rail and robotic systems will be installed on ground. The system will then launch and arrive at Gateway in early 2024 and will be fully operational by late 2024. Once integrated, the robotic system could also assist with constructing the interior outfitting of Gateway. So we identified 18 total risks associated with this project, which include various robotic component failures, robotic mobility system failures, robot crew interaction failures, and programmatic risks. The table on this slide shows the likelihood and severity of consequence of each risk, with the least likely and least severe risks represented by green blocks, transitioning to the most likely and most severe risks represented by red blocks. Our most critical tasks are listed on this slide, including the robot impeding crew objectives, moving without warning, or possibly damaging Gateway. One main mitigation added was incorporating a braking system to the robot to prevent unwanted movement. So one of our level 1 requirements was that our design had to be within a $2 million budget, so this slide shows a breakdown of our budget. Since the robotic system is modeled after the Ranger TSX robot, the budget for this proposed robotic system is based on the actual cost of replicating our TSX. Since this has been done before in the Space Systems Laboratory, this cost is very accurate. The software cost approximation is based off of 2 years of programmer effort making any necessary edits to the flight software. All other cost approximations were based off of various industry data. So to summarize this project, supervised robotic maintenance and repair of a space habitat will allow that habitat to remain operational while uncrewed for longer durations. This is extremely important for the Lunar Gateway, since it will be uncrewed for 11 months at a time. This robotic operation also allows crew members to maximize the amount of time spent on conducting science experiments and increase the amount of discoveries they're able to make. In addition, the improved cargo transfer bag logistical system that we presented will also save the crew time and even enable purely robotic resupply missions. So to recap the most innovative aspects of our proposed design, we developed an AprilTag identification system for logistics management and space habitat situational awareness. We designed, fabricated, and tested a Nika-drone semi-permanent electromagnetic end effector. We created a custom GUI for simplifying complex maneuvers and expediting operations. We integrated collision-aware motion planning that is critical for tight environments like the Lunar Gateway. And lastly, we designed a rail system to allow for robot mobility through Gateway and other space habitats. And finally, our ultimate vision is to enable robots to work both independently and safely alongside astronauts in a cluttered environment similar to this image of the ISS, which would ultimately allow for more advancements in space exploration. So we would like to thank our faculty advisors, Dr. David Aiken and Dr. Mary Bowden, the UMD Space Systems Laboratory for hosting this project, the UMD Robotics Realization Lab for Baxter testing, the UMD Gemstone Honors College for making this all possible, and NASA RASC-AL for selecting our proposal for Theme 5. So now on to questions.